Welcome back, guys, and in this tutorial we're going to be moving on from geometric sequences to look at geometric series. So as we said in the last one, a series is when we're trying to add all of the terms of a sequence together. So on page 22 again in your log tables here, you're going to find our next formula for the geometric series, which is the SN formula, which is a reminder, this means the sum of formula A by 1 minus or to the power of n by 1 minus or. Now this formula in particular, guys, is going to be crucial when we start looking at financial maths, if you want to write that in beside it. Okay, so if we look at this, we're going to do example 1 here, where we're asked to find T5 and S5 of each of the following. Now in part 1, we have the sequence 1 plus 3 plus 9, but we know it's a series as there's a plus in between. To find Tn, we still just use our normal formula here, which is going to be Tn is equal to A by or to the power of n minus 1. So T5 would be our first term, which is 1, by our common ratio, which I can see 3 over 1 is 3, to the power of 5 minus 1. So I really have 1 by 3 to the power of 4, and 1 by 3 to the power of 4 gives me 81. Which means my fifth term in the sequence is 81. However, if we want to find Sn, which is the sum of the series, we have A by 1 minus or to the power of n all over 1 minus or. So to find S5, what we're going to have here is 1 by 1 minus 3 to the power of 5. And brackets are going to be very important here when we put it into our calculators. All over 1 minus 3. So again, fraction button on our calculator, 1 bracket, 1 minus 3 bracket to the power of 5, press across and bracket, down and 1 minus 3 gives me 121, which means the sum of the first 5 terms, added together, gives me 121. So now we're going to look at the second one here. So for part 2 again, what I'll see here is to find T5, we're going to use our formula. Tn is equal to A or to the power of n minus 1. So T5 would be our first term, which is 1 again, by or, which would be a quarter over 1, which is just a quarter, to n minus 1, so 5 minus 1. So here I have 1 by a quarter to the power of 5, which again onto our calculator, to the power of 4, which again on our calculators here is 1 over 4 to the power of 4 gives me 1 over 256. So my fifth term is 1 over 256, compared to my Sn, which is A by 1 minus or to the power of n, all over 1 minus or, which means I have S5 is A, which is 1, by 1 minus 1 over 4 to the power of 5, all over 1 minus a quarter. So again, onto our calculators here, we're going to have 1 by 1 minus, to call it out here, fraction button, 1 by 1 minus, in brackets, 1 over 4 to the power of 5, close your bracket, all over 1 minus 1 over 4, which gives me 341 all over 256. And then this is what the addition of the first 5 terms would give me. So take a second, guys, to get used to this new formula, and then when you're ready, we're going to move on here to example 2, which is similar again to a question we looked at before when we were looking at the geometric series. It says, sequences. It says in a geometric series, T3 is equal to 32. So again, I'm going to start with T3 is equal to 32 and T6 is equal to 4. And what we want to do in part 1 is we want to find A and or. So we're going to use our Tn formula, which our hint is given by T3 and T6, term 3 and term 6. So I have Tn is equal to A or to the power of n minus 1. So my value is 32 is equal to A or, my term is 3, so 3 minus 1. So we have 32 is equal to A or squared. Then I'm going to do the same thing over here, substituting in my same values. So I have 4 by A or to the power of 6 minus 1. So 4A or to the power of 5. Again, it's easier to isolate A on this side. So I'm going to divide both sides by or squared, which is going to give me 32 over or squared is equal to A. which I'm going to substitute in over here. So I have 4 is equal to 32 over r squared by r to the power of 5. Again, I'm going to see here 5 take away 2, which is my rule with indices. It's going to leave me with r to the power of 3. So now I'm going to have 4 is equal to 32 r cubed. Divide both sides here by 32 to get rid of the multiplying, which is going to give me 1 over 8. So again, here now I have 1 over 8 is equal to r cubed. And to get rid of my cubed, we always do the inverse, which I know is going to be a cubed root, and I end up with a half is equal to r. So now I'm going to bring this back and I'm going to substitute it in. So if 32 is equal to a half squared over a. So again here what I'm going to have is 32 divided by 1 over 4, which gives me 128 is equal to a. And now this is where we have our sequence. So we have a and r. So the important part now for part 2 is when it says find S8. To find S8, I know I'm using my Sn formula, which is the sum of the first 8 terms. So I have a by 1 minus r to the power of n, all over 1 minus r. So my n is going to be 8, my a is going to be 128, and my r is going to be a half. So I have 128 by 1 minus a half to the power of n, which I know is 8, all over 1 minus a half. And we put the whole thing into our calculator again. So fraction button, 128 bracket 1 minus bracket a half, close your bracket, to the power of 8 all over 1 minus a half, which gives me 225 as my answer here. Okay, so take a second here, go back through this again before we move on to our last new formula for geometric series. So on the very bottom, guys, of page 22 in your log tables, what you'll see is it says for a geometric series where the modulus of r is less than or equal to 1. So again, this is extremely important here. Can you highlight, underline, do something in your log tables where it says the modulus of r is less than 1? That means whether it's plus or minus, the common ratio has to be less than 1, which means it has to be a fraction. So what that really means here is that r has to be a fraction of some form. Okay? So it says the limit as Sn approaches infinity, which is really my S to infinity, is given by a over 1 minus r, which usually tends to come up if it says that the series is unlimited or it goes to infinity, like it says here. Find the sum to infinity of the geometric series 16 plus 12 plus 9. So I can see here that if I want to find r, it's going to be term 2 over term 1. So it's going to be 12 over 16, which is going to give me 3 over 4. I can see that a is nice and simply 16. So to find s to infinity, we're just going to sub it in here. So I have a over 1 minus r. So instead of a, I put in 16, all over 1 minus 3 over 4. So I have 16 over a quarter, which again, you can just use your calculator for this bit, guys, if you prefer. And 16 divided by a quarter gives me 64. Which means as this series gets smaller and smaller and smaller and smaller, and they're all added together, the number it's approaching is 64. Which you'll remember when we studied limits, guys, in differentiation. Now, last one when you're ready. So again, you can pause the video here to add that little one in. And the last one when you're ready is looking at example 4, which is how we can use the limit to infinity to write reoccurring decimals as a fraction. So it says write the reoccurring decimals 0.23 recurring. And remember, we know that these dot dots is what stands for recurring as a fraction in the form a over b, where a and b are elements of n. And we know that n stands for natural numbers. Now, what a reoccurring decimal means, guys, again, is 0.23 recurring is the same as having 0.2323232323, and it just keeps going. Now we can actually write this as a series, where the first decimal here would be 23 over 100, because again, this is my tenths, this is my hundredths. So my first one would be 23 over 100. My second one would be 23 over, this is my thousands, this is my 10,000s. So plus 23 over 10,000. You can see I'm just adding 2 zeros each time, which means the next one would be 23 over a million. Because again, I'm just adding 2 zeros each time. So you have 1, 2, 3, 4, 5, 6. Oh, sorry, 10 million. Okay. Now, and then we're looking at the next one. So we added 2 zeros here, which was 4. No, I was right the first time. Sorry guys, which is just a million. Okay. Now, so we have a million here, and then it keeps going. So what that means is A is 23 over 100, my first term. Or is going to be term 2 over term 1, which is 23 over 10,000, all over 23 over 100, which we can see visibly is just 1 over 100. Okay, so now to find my reoccurring decimal, this would continue indefinitely to infinity, which is why we're going to use s to infinity is equal to a over 1 minus or, where a is 23 over 100, all over 1 minus 1 over 100, which is or. So we have 23 over 100, which is equal to 99 over 100 on bottom, which again, when you put this into your calculators, guys, you're going to get 23 over 99. So we can say, therefore, 0.23 recurring is equal to 23 over 99. And again, guys, if you press 23 over 99 into your calculator and press SD to get your decimal, you should see 0.23 recurring. And this is a nice little question when it comes up. So, again, I'd pause the video here, add this into our notes, make sure we go over it and that we're happy with it, and then we will finish up by revising the last little bit of Junior Cert Maths in